Hi, and thanks for joining us for another video on thunderstorms. In this one, we're going to talk about classification schemes, and we're working our way through cell configuration. So this video will be all about supercells. And supercells, of course, are dangerous storms. They are one big massive storm that rotates, typically about 25 miles across. Little single cell air mass thunderstorms are about a mile or two across. This can be up to 25 miles or so. And they last a long time. The hazards that are associated with supercells, of course, are tornadoes, but also they produce strong winds and some of the biggest hail you'll ever see. They develop in a sheared atmosphere, so the wind changes with height, not only speed, but also you have directional shear. So that, I'll show you a sounding here from the tornado at Norman, Oklahoma back in 2013. Here you go. Shows you at the surface the winds are out of the south. As you move up through the atmosphere, the winds become from the southwest. And then at the jet stream levels, the winds are more from the west. And that's typical of what you see with supercells. Of course, supercells develop in the maritime tropical air. That's out ahead of a cold front, but behind the warm front. You get moist air there. And supercells can be individual or discrete, all by themselves. Here you see one by itself, but there is one just to the north of it. This is the one that went through Siren, Wisconsin years ago and tore up the town. You can also have a line of supercells, and that's what's shown here across Oklahoma. Also, we had a line of supercells come through eastern North Dakota in 2007. One of the storms hit Northwood and did quite a bit of damage. That was an EF4 tornado. And then the way a supercell works is that, of course, the updraft rotates because of the shear in the atmosphere. The shear gets tilted and you have a rotating updraft. That's what we call the mesocyclone. So the updraft is rotating, and that rotating updraft you can see in Doppler radar, and it's usually the precursor to a tornado. The rotating updraft mesocyclone is usually pretty wide. It's about maybe 5 or 6 miles in diameter, whereas the tornado by itself, of course, tornadoes are not much bigger than 1 mile, and typically much smaller, usually only less than a quarter mile, maybe an eighth of a mile across. Some characteristics that you should note of supercells: they have a very strong radar reflectivity gradient, meaning that the colors will change very rapidly. That will help you identify them, as well as also help you figure out where the hail is, the large hail. Typically, large hail falls closest to the updraft because the updraft is supporting the hail. When it gets so big it can't be supported anymore, it falls through the updraft and falls out of the storm. Smaller hail, of course, can be found throughout the anvil, so it's not good to fly through an anvil downwind of a supercell thunderstorm. Also, another thing is the inflow notch. What you see here, this picture is it's looking down on a thunderstorm, kind of like a satellite view, but they've superimposed upon that different areas of precipitation, and they're showing you where the large hail and the small hail is, and then as you progressively move out from the updraft, you get rain, and then heavy rain, and then light rain. Tornadoes found in the updraft, and kind of tucked in the updraft there. We'll talk more about that here in a little bit. And then you can see also the flanking line. And you see these fronts, and what those fronts are. The one that's coming out of the storm, out ahead of the storm, is the gust front. It's and it says right there gust front, but that's the forward flank, and we're going to talk about that in the next slide. And on the back side, you've got the rear flank downdraft. The inflow notch is where the air is flowing in, and that's represented by a warm front on this picture. So here's some pictures that help you visualize the downdrafts. There's two downdrafts actually with supercells. You've got the forward flank downdraft. It's on the forward side of the storm. In this case, the storm is probably moving to the north and east. And so out ahead of the storm, you've got a downdraft, but on the back side, you also have a downdraft, and that downdraft is called the rear flank downdraft. And the rear flank downdraft is instrumental in helping produce the tornado. And as I said before, you have that inflow, the air flowing in. That's where that was the warm front that we saw earlier on the previous slide. And then finally, you can see how the precipitation is wrapping around the backside of the updraft. And that's where you have the hook echo. That's the distinctive hook echo that tells you there's possibly a tornado with this storm. Supercells can be further classified into the classic, the HP, and the LP, low precipitation and heavy precipitation. And as the name implies, heavy precipitation means it has more precip, and low precipitation means it has less precip. So here's an artist version of the classic supercell showing the overshooting top and the anvil, precipitation out ahead of the storm, perhaps hail closer to the storm. As you get towards the updraft, you'll see the wall cloud, the lowering, and usually there's a beaver's tail, a tail that points towards the precipitation. But on the backside, you typically don't have much precipitation. It's what storm chasers call the rain-free base. And this is to the right, you see an artist's version of what it looks like, and you can see the wall cloud and the lowering. And then a picture that was taken by Roger Edwards, who worked at the Severe Storm Labs for years, showing the lowering in the cloud and the precipitation out ahead of the storm. Classic supercell, we looked at this picture already looking down, but you can see stronger rate of returns around the updraft, and then you can see the hook coming around the back, and then also the inflow that results in the updraft or feeds the updraft. Here's an HP supercell. HP supercells, you remember there was no rain on the backside, but with HP supercells, with the classic, there is no rain on the backside. But with the HP supercells, there is precipitation on the backside. So it makes it a little bit harder to find that wall cloud. Here's an artist version of what it looks like. Really hard to find that wall cloud. But on the right, Al Moeller took this picture down across Texas, and it shows a really well developed, the supercell, HP supercell. This is what it would look like on basically radar and also satellite looking down. You can see that the hook is not as well defined. It's kind of just a big blob of precipitation. And then finally, the LP supercell. And I should back up and say that the HP supercells are typically found in areas where there's a lot of moisture in the atmosphere. You tend to find them very frequently along the Texas coast, but also across Louisiana, Mississippi, Alabama, even into Tennessee and Arkansas at times. But LP supercells, of course, as the name implies, there's not much precipitation. So you tend to find these in drier climates, and usually you find them in West Texas, Western Kansas, Western Nebraska, even in Colorado and New Mexico. Very frequently you'll find these. So as this picture shows, of course, you got the overshooting top and the anvil, but you got precipitation that kind of separates from the main updraft, and you can't see it very well. And then they are really strange looking storms. Some people call these bell-shaped storms. I'll show you some pictures here in a little bit. There you go. There's the artist version of what a LP supercell should look like. And then there's a picture of Roger Edwards. And you can see that that lowering is separated from the main cloud and precipitation. So it's these are really beautiful storms. And then looking on a radar, you don't see the hook echo very well. It's just kind of a blob of precip, and that's about it. So some characteristics of supercells. Supercells typically, if they're severe, tend to move to the right of the mid-level winds. Remember we talked about how most storms kind of move the same direction as the 700 millibar or the 10,000 foot winds. Supercells tend to move to the right. So if you see a right mover, significant right mover, then you know that that is a dangerous storm. Other things help you identify a supercell, the overshooting tops, there's a satellite video picture of May 3rd, 1999, where the town of Moore, Oklahoma was devastated by an F5 tornado. And then on the left you can see a supercell with the overshooting top coming out of the anvil. And then, of course, the hook echo helps you identify where a tornado is. Usually these hook echoes are very small, but also you can see an inflow notch right by the hook echo. You kind of see a little notch or a little area that tells you where the moisture is being fed, and that's usually the strongest gradient in the storm, the strongest change in radar reflectivity. And then one other thing, if you're looking at if you're looking at radar, you can tell the storm is a supercell by looking for the V notch. If you see this V notch, that's where the air is diverging around the updraft or the upper level updraft. So that tells you that that is a supercell. Supercells, of course, are prolific tornado producers and also large hail producers. We're going to look at a case. This is May 3rd, 1999. Moore, Oklahoma was devastated by this tornado. This is a supercell. They had many supercells on this particular day, but this one is pretty obvious. It is a classic supercell. You can see the hook is already well developed, and we're going to do a cross section. What we're looking at right now is about 3,000 foot for the storm where it is. But this is your half a degree elevation, in other words, your base reflectivity. Going up through the storm, we're going to take a cross section, of course, from A to B, but this is at approximately, I think, 13,000 feet, because that's about where the freezing level is. And then this is at about 33,000 feet up high. And you can see that the storm kind of leans with height. You're looking at, before at AB you had strong radar returns, and now you're just on the edge of the radar returns. So there is strong shear with the storm, and it's leaning. Whenever a storm leans like that, that means that it's a dangerous storm. So here's the sounding for that particular day. You can see that the freezing level was about 12.5. The balloon didn't go all the way up through the atmosphere. This is a 0Z balloon. And the tornado was occurring as they sent up the balloon, so something happened to the balloon. This is what it looked like in cross section from point A to point B, and you can see the overhang at point B. If you head to the left, you can see that notch, and that is actually the updraft that's feeding the storm. And then that area of red that's kind of hanging over the updraft at about maybe 21 or between 14 and 21,000 feet is what we call the bounded weak echo region, and that's a region that's favored for hail embryo development. On the back side, you can see heavy precipitation that's wrapping around with the tornado. The storm is well above 42,000 feet. The radar never did determine the tops because the storm was so close to the radar, and the storm was so tall that they couldn't get it to the top. So that's supercells in a nutshell. It's kind of an annotated version. I like to spend more time discussing these, and if you're in class, we'll talk more about this.